Hey guys, this is Emerald Fire. Today I have three new random number functions updated for 1.16. To use them, all you have to do is download the data pack in the description and set math in 1 on objective EM as the lower bound of the range, set math in 2 as the upper bound of the range, and then run the random number function of your choice to get a number from 0 to 99 inclusive. The upper range number is not included in the range. The three different random number functions are randomp, random, and randomu. The difference between them is that randomp is a pseudo-random number generator that only uses scoreboard commands. So this one would be the fastest and is probably the one that you should use if you're just making a mini game or something. Random is a random number generator function that is a true random number rather than a pseudo-random number generator, and it uses predicates, but still no blocks, entities, or actual loot tables. Then randomu is a true random number generator that always has a uniform distribution compared to an approximately uniform distribution for small numbers. That uses loot tables and an entity to find the random number. I'll talk more about the differences between these functions in the second half of the video. If you're not interested, you can just go ahead and download the data pack from the description, use any one that you like, and you're good to go. I should mention that randomp is based on a pseudorandom number function that CloudWolf first showed. I had to make some modifications to it. The one in CloudWolf's video always alternated between even and odd numbers because instead of using the upper or middle bits of the generated output, he used the entire one, which results in alternating between even and odd. For this one, I instead generate two random numbers, use the middle 16 bits of each of them to combine and make a 32-bit random number generator. Yeah. So the ranges for this random function are anywhere. It can go into the negatives, so 500 and plus 100, then we'll get random number between those two ranges. We can do things in the positives, and we have very large random number ranges. So let's go with 500 to 10,000, and you see it works just fine. And this can go actually all the way up to the limit of scoreboard. The maximum range for finding a random number is 2 to the 31 minus 1. So that is the entire positive half of the scoreboard. You can also run these functions as many times as you want within the same tick. For the rest of this video, I'll be talking about the differences between these three functions. The first difference I'll talk about is between randomp and random. The main difference here is that this is a pseudo-random number generator and this is a true random number generator. A pseudo-random number generator is a number that is generated by a computer algorithm. It starts with a seed and then it performs operations on that seed to get the next random numbers. And now you may be wondering, how can I possibly call this a true random number when Minecraft is running inside of a computer that's doing this very thing? Well, within the context of Minecraft, I'm defining a true random number as one that Minecraft says is true. For example, the random choices of a dispenser to spit out an item, or the random entity sort selector, or the random loot dropped by a loot table. Those all come from the random number generator that the engine Minecraft is running on generates. So for the sake of this video and for any future random number generator functions I'll put out, this qualifies as true random in my book. Now, pseudo-random number generator is something where my seed number is in scoreboard, and every time you run this command, it's going to perform operations on that seed to get the next random number and then copy it over to math out and fit it within the range. So that's what I would call a pseudo-random number. And the difference between pseudo-random and true random is that if you know what seed you started with, you're able to predict all future random numbers that this generator will put out. For applications like cryptography and security, this is not so good because if anyone manages to crack the seed, then they've pretty much figured out your entire security encryption operation that you're using those random numbers for. You can actually sort of do this in Minecraft. EarthComputer made a video a while back where he made a tool to crack the seed of enchantments. So you do a few enchantments, and then you put the output into his tool, and he figures out what enchantments you could possibly have next, and it includes a guide on how to get the best enchantments for your current seed. So yeah, that's one fun thing you can do with pseudorandom numbers. However, a true random number is something derived from the environment. Something like if you have in real life a camera pointed at a wall of lava lamps and you observe the positions of the bubbles inside the lamps at all times and use that to generate a random number. That comes from the external environment, and it's impossible for an outside computer to predict that. Both of these are an approximately uniform distribution for small numbers. So what I mean by that is these are generating 32-bit random numbers, which is pretty much the limit because that is the number of bits in a scoreboard value. You could, of course, generate more and more random numbers to get more bits, but it always would be approximately uniform when you fit it into a range because it's going to be a power of 2 since you're generating it using bits. And then you have to do modulus division to fit it into your range. And for larger numbers, this is going to give a bias towards lower numbers in that range. So for small numbers, it's approximately uniform and you won't even notice the difference. But for large numbers, it could start to get a little bit of bias. You'd have to go really large. And that's where randommu comes in. This is a truly uniform function because it uses loot tables in a way that guarantees that the number will always be uniformly distributed in your range. Because it uses loot tables and an entity, it is a little more intensive on Minecraft's actual processor, but it still runs really, really fast. So like you could run this every single tick and not even know about this. Actually, we can do a benchmark test right now. I have 99 armor stands in that hole. With me, that makes 100 entities, so I'll be running this command 100 times per tick. We'll start out by doing random p. To see the effect it has on the game, keep your eye on the ms ticks up here in the corner. If that ever reaches 50, that's when the game starts to lag. I'll press this button, and you see with random p, it gets up to 2 or 3 ms ticks. If we switch that over to random, it goes a little higher, usually like 6, 7, 8 ms ticks. Keep in mind I'm also recording my screen, so it's a little bit higher. Then if we go to randommu and hit this, it gets higher, and this time it's going up to like 20 some, close to 30. So even at running 100 times per tick for many ticks in a row, it doesn't even get to the point of lagging the game. But there are definitely performance differences that you should keep in mind if you're making a map or a minigame with these. To demonstrate the difference a uniformly distributed random number can make, I have this setup over here that will pick a random number from 0 to 3/4 of the maximum range size for a random number using this function. And then it will run random, and if the random number is in the lower 1/3 of the output range, it's going to add 1 to a player called lower third. If it's in the middle, it'll add 1 to middle third, and if it's in the upper, it'll add 1 to upper third. Because each of these are 1/3 of the total range, it should be even for each of these for a large number of dice rolls if the distribution is truly uniform. So let's run this here. And you'll see after I hold this button down for a while that upper and lower are gaining a significant lead over the middle third. Let's reset this and try again. If I press it and hold it down for a while, you can see again that upper and lower are fighting it out, but middle third is lagging behind. So what's up with that? If we consider our entire number line to be divided up into chunks of powers of 2, I'll divide it up into 2 to the 29 here because the total scoreboard is 2 to the 32. Then we get numbers from -4 to +4. And then let's say we want our random number range to be 2. 2 divides into the total number here, so when we try to set it into this range, we get nicely divided buckets here that we can then map each number within this bucket to a number within the output range. However, what if we tried to do something that did not divide the total range? If we set our range to 3, then when we divide this number line up into buckets, you see the top is only 1/3 of a bucket, and the rest of this bucket would be off the number line, so it doesn't get used. The same thing on the other end, it's only 1/3 of this bucket here, and then the other part of this bucket isn't used. Then if we try to map those numbers into our output range, we'll say iron is the lower third, gold is middle, and diamond is upper. Then we have 1, 2, 3 iron blocks, 1, 2, 3 diamond blocks, but only 2 gold blocks. So we end up with a distribution that looks like this, where the middle third only has about 2/3 of the output as the lower or the upper. If you were doing some kind of game like a casino or a gambling simulator, then you would want your odds to be as evenly distributed as possible to make sure that players couldn't game the system or that the house wouldn't be given an unfair advantage over the players. To fix this, you can use randomU. When I try this test again using my uniform function, you'll see that all the numbers stay approximately equal. In this case, upper third is lagging behind a little bit, but if we let it run for long enough, it'll eventually average out. Reset it again, and you'll see that the positions of middle, lower, and upper this time are pretty much randomly different from what it was before. They keep fighting each other, and there's no clear winner here. To accomplish this, I used loot tables and the weights that you can give to individual buckets of loot in a loot table. I imagine the loot table buckets as the bits in the random numbers that I mentioned earlier. To fix their distribution, we can give weights to the buckets according to the number of numbers within that bucket. To make that a little clearer, here, if we wanted to pick a random number with a range size of 9, then we would add 1 plus 8 equals 9. We would want to use these 2 loot buckets. And to remove the other buckets from consideration, all we have to do is make a scoreboard value that does not satisfy a condition on these buckets, so they're no longer considered in the total weight. Then, if this has a weight of 1 and this has a weight of 8, we get a total weight of 9. So our choice of number will be equal to whichever number is in the bucket, or it will be proportional to whichever number is in the bucket. So we have one number in this bucket, and it has a 1 in 9 chance of being chosen. We have 8 numbers in this bucket, and it has an 8 in 9 chance of being chosen. Same if we were to switch this to 11. Then we would have a 1 in 11, 2 in 11 chance, and then over here we have an 8 in 11 chance, because 1 plus 2 plus 8 equals 11. Then, within these buckets, this is now a power of 2, which, as I explained before, allows us to get a perfectly uniform distribution within that bucket. The end result is a random number that is perfectly uniformly distributed across its range. So we have numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The 8 numbers in this bucket will have an 8 in 11 chance of being chosen. Then within this bucket, we'll do our random number roll, and each of the numbers inside of it has an equal chance of being chosen. So if you add those odds together, we get a 1 in 11 chance for each individual block. I hope that makes sense. I had fun designing this random number generator with the loot tables. It's cool that we can finally do a uniformly distributed random number like this in Java Edition without setting the range specifically beforehand. Because previously you could do random numbers uniformly, but you'd have to say what range you want when you were writing the function. So you have to just like make the function do a random number from 1 to 100, and you couldn't set a custom range. Now, Bedrock Edition actually has a random number function built into the scoreboard. So if that ever gets ported to Java, then we won't need to do any of this nonsense anymore. But until then, I'll keep on making random number generator functions as good as they can possibly be. Well, thanks for sticking around to the end of the video. I hope you enjoyed my explanation of random numbers, and I hope you'll find these functions useful. Thanks for watching, and I'll see you in the next video.